Hello everyone, right, what I'm going to just do in this video is a quick run through of how to run a chi-square analysis in SPSS. This is the second time I recorded this video. I recorded it once, but I did it yesterday afternoon and the quality wasn't very good, so I'm going to give it another go now. Yeah, okay, so recording or conducting chi-square analysis in SPSS. What I've got here is a SPSS data file open on my screen in front of me, and it's got two categorical variables and frequency counts falling into each of these categories. So the first thing we've got is made up data, essentially. First thing we've got is a variable called condition, and that's experimental condition. So participants took part in a study and they did it in a seen or an unseen condition. So those are the two levels of that particular categorical variable. So they completed the study whilst they were in the same room as other people, so they could see other people, or they did it in a room by themselves in isolation. Okay, the second categorical variable there is labeled Nash equilibrium. Okay, and that records whether in each of those conditions an individual, when they were taking part in the study, they had to make decisions, and whether they used a Nash equilibrium strategy when making a decision. So yes, they used a Nash equilibrium strategy, or no, they didn't. So you can see we've got a 2x2 contingency table, effectively. And the third variable there is the frequency. So that's the frequency of participants falling into each of those categories. So 28 people in the seen condition played a Nash equilibrium, 10 people in the seen condition didn't, etc. So the data here, in the way that it's formatted in this particular data frame, this particular set of data, is a bit unusual. It's not in the long and short format, which is most common and generally what I prefer. The way it's set up here is slightly different, and the frequency counts of individuals are a separate. They've been created as a separate variable in themselves. So in order to analyze this data using a chi-square analysis, there's an additional, because I've set the data up in this way, there's an additional step we need to do, and that's we need to weight cases by the frequency variable. So to do that, to make sure we get our analysis correct, we click on data. At the bottom of this drop down menu, you've got weight cases. If I click on that, it brings up this pop-up box, and you can see there by default it's set to do not weight cases, but in this case we're going to weight cases, and it tells you to put the frequency variable in here. So frequency variable, so that's all we got to do. We're going to select weight cases and move the frequency variable over to that box, click OK, and our output window will show that it's weighted by frequency, which is good. Let's go back to the data file. Okay, so now that's done, we're pretty safe to run our chi-square analysis in SPSS. And the way that we do that is we click on Analyze. To access this type of categorical analysis, we do it through the Descriptive Statistics menu. We click on Descriptives and then cross tabs, and it brings up this pop-up box. So we now need to put one of our categorical variables in the rows and one in the columns. I'm going to put experimental condition in the rows and Nash equilibrium condition in the columns. Yeah. So yes, no in the columns, and seen unseen is going to be in the rows. Okay, so we've done that. Next, we want to click on the statistics button and select a couple of options. We'll ask for a chi-square analysis. That's what we're interested in. I'm going to also select phi and Kramer's V. So then Kramer's V, as you should remember, is a measure of effect size. Phi is also a measure of effect size. We're not necessarily going to need them in this case because we can work out the odds ratio we've got a 2x2 contingency table, so it's kind of quite easy to work out the odds ratio. But I'll select them anyway. We probably won't make use of them in this case. Okay, so if we click on continue, the next button to click on is cells, and we're going to select a number of options from this kind of cells menu. we're going to ask, it's given us observed counts, which we want. They're the observed counts to the frequencies in our data. We're going to ask for the expected counts as well. I'm going to ask it for row, column, and total percentages. So it's going to give us a contingency table that's quite busy. There'll be a lot of rows and things on it. I'm also going to ask for standardized residuals, because that will be useful when we're looking at trying to interpret where significant differences are if we have a significant chi-square. And I'm also going to ask it to compare column proportions and adjust using the Bonferroni method if necessary, if we've got multiple. If we have more and more rows and we're doing multiple comparisons. So if I click continue, I'll bring us back to our main box. I'm going to click on OK, and it'll run the analysis for us. And in our output window, it will give us a variety of different tables. It'll give us 4, in fact. The first one's just showing how many cases we've got, 200. The second one is this very busy contingency table. So you can see we've got the seen and unseen condition. The 2 levels are experimental condition, and no and yes for the participant played in Nash equilibrium. So the 2 levels of in the columns, the 2 levels of our Nash equilibrium categorical variable. Okay, and we've got counts in there. These are their observed counts, 10, 28, this should 114, 48. This should look familiar because it was the same on the data set. It's also given us the expected count, so we can look to see if they appear quite different in some cases to what our observed count is. But before we do anything else with that table, the first thing we really need to think about is whether we've got a significant chi-square test result. So are these 2 variables significantly associated? And if we scroll down to the chi-square test table, we're going to use Pearson's chi-square in this case, and it gives us a test statistic chi-square of 25.356. So if we round that, that's 25.36. If we round it to 2 decimal places, we've got a p-value significance level of p is less than 0.001. So less than 1 in 1,000, highly significant result. So these 2, according to Pearson's chi-square, these 2 variables are significantly associated. Okay, so now that we know that, we can go back and look at our contingency table and say, well, they're significantly associated. So, in what way? So, what are the relationships of interest, or which categories might differ from which others? And there were a couple of things we asked for. We asked SPSS to compare column proportions. And if you look underneath the table, there's a little note saying each subscript letter denotes a subset of participant played in Nash equilibrium whose column proportions do not differ significantly from each other at the 0.05 level. Okay, so if we look at our counts, we've got a little subscript A next to the 10 and a subscript B next to the 28. If we go down, and the no condition for the unseen, we've got an A next to 114 and B next to 48. So if the letters are the same, then those column proportions don't significantly differ. But if they're different, they do. So A shows that the proportions are significant. The proportions in this yes column are significantly different to the proportions in this no column. And to interpret exactly to make sense of that, essentially, what we would need to look at is this particular line here where it says percentage within participant played in Nash equilibrium. So remember, the columns are participant played in Nash equilibrium, and it's looking at the proportion of individuals in the column in the seen condition that's played in Nash equilibrium compared to the total column proportion for yes played in Nash equilibrium, and likewise for no, the proportion that didn't play in Nash equilibrium compared to the total column proportion. And what we're seeing here is, because A and B are different, we're seeing that these 36.8 is the proportions of participants who did and didn't play in Nash equilibrium in the seen condition is significantly different. And we're seeing a similar thing if we compare these two, 63.2 to 91.9. So that it, as I mentioned before, it's not. That's telling us that within the unseen condition, there's a significant difference between the proportions that didn't and the proportions that did, but it's not always easy to tell. If you look, okay, could you say 91.9 is significantly different to 23.2 without SPSS helping you with that, with these subscript letters? So we've got a significant chi-square. We've got column proportions that differ, but what we're interested in is where the significant differences are. Which of the counts, our actual counts, differ significantly from the expected counts in each of our cells. And to answer that, we asked for standardized residuals, and this is quite helpful. So we've got negative 2.8 and 3.6 as our standardized residuals here. For participants who didn't play Nash equilibrium in the seen condition, we've got a standardized residual of negative. For 10 individuals, that represents a standardized residual of negative 2.8. So this is essentially like a z-score. It is a z-score, and it's telling us that significantly fewer of our participants than expected by chance in the seen condition didn't play a Nash equilibrium. And we know it's significant because it's greater. It's actually significant at the p is less than 0.01 level, because it's greater than, so it's actually less than negative 2.53 standard deviations. Okay. If we now look at in the seen condition participants that did play a Nash equilibrium, so we've got a count of 28 and a standardized residual for that of 3.6. Okay, so this time what this 3.6 is telling us that significantly more people in the seen condition played a Nash equilibrium than we would expect by chance. So effectively it's telling us the observed frequency is significantly greater than the expected frequency, and that is a standard deviation of 3.6. And if hopefully you remember, we've got these different cutoff points. If it's greater than plus or minus 1.96, it's significant at the 0.05 level. If it's greater than or less than 2.53, then it's significant at the 0.01 level. If it's greater than or less than 3.29, then it's significant at the 0.001 level, and this is bigger than that. So we've got at the p is less than 0.001 level, we've got significantly more individuals in the seen condition that did play a Nash equilibrium. Okay, so now we can compare the counts and the expected counts in the unseen condition, 114 compared to 148 compared to 61.6. So they look different, but are they significantly different? Well, if we look at the standardized residuals, that will tell us the answer to that. So we've got a standardized residual of 1.4 for the unseen condition participants who did not play a Nash equilibrium. Right, so what that's telling us is more people played a Nash equilibrium more people didn't play a Nash equilibrium than we would expect by chance, than we would expect based on the expected counts in the unseen condition, but it isn't statistically significant. So it's not a significant result, because 1.4 is less than the plus 1.96 we would need it to be in order for it to be significant at the p is less than 0.05 level. Okay, so where more people didn't play a Nash equilibrium than expected in the unseen condition, but it wasn't significant. And if we look at individuals who did in the unseen condition play a Nash equilibrium, the expected count was 61.6, but the count was 48. And what we're seeing there is a standardized residual of negative 1.7. So fewer than expected did, but again, that is a bigger number than negative 1.96. So it's not significant at the p is less than 0.05 level. So what this is telling us, we've got a significant chi-square result. These two variables are significantly associated, and when we break that down to try to figure out what is contributing to the chi-square significant chi-square result, what we find is that in the scene condition, significantly fewer people than expected didn't play in a Nash equilibrium, and significantly more people than expected did play a Nash equilibrium than we would expect by chance. But the unseen condition isn't contributing to the significant chi-square result. Okay, hopefully that makes sense. The last table, which I said we wouldn't mention, we probably wouldn't use, was this symmetric measures. Gives us our measure of effect size. Because we've got a 2x2 contingency table, we could work out the odds ratio. And if we did that, if we calculated the odds ratio here, what we would find is that the odds of playing a Nash equilibrium are about 6.5 times greater if you're in the seen condition than if you're in the unseen condition. Okay, right.